Yes, welcome to second half of Christian Gaetz talk. Please take it away.
All right, very good. So I had just stated this theorem, and then I was going to start explaining some of the ideas that go into the proof. Um, so this idea, so we want to prove that this coefficient is a combinatorial, and in fact, we will give a combinatorial interpretation for it. So Patimo was the first to use the definition I'm about to describe. So I'll write EUV for the set of cover relations of the interval U to V. And a subset of those edges is called diamond closed if whenever it contains two adjacent edges from some diamond, it also contains the other two. So Bruhat order has lots of intervals of height 2. They all look like diamonds like this. And what I'm saying is that if I contain these two in X, then I must also contain these other two. Or if I contained the top two, then I would have to contain the bottom two. So by adjacent, I mean consecutive in the cyclic ordering of these edges. So X bar denotes the smallest diamond closed set containing X. So it's the diamond closure of X. And Patimo defined GUV as the smallest size of a diamond generating set for UV, meaning a set whose diamond closure contains every edge.
Question.
Yes.
So, uh, you say cyclic order on the edges as if you have a favored planar embedding of the Hasse diagram?
Um, I just mean, okay, maybe that was not the right way of saying it. Two edges which share a vertex. If I have those two, then I must have the other two of the diamond. Um,
No.
what it does not include is if I have two opposite edges of the diamond, that doesn't entail that I have the other two. Um, okay, so in this interval, the three red edges are actually a diamond generating set for this interval. So we can play a little game. So I start with these three. Now I can look, for example, at this diamond here. I have the bottom two edges of it, so I must also have those two. Um, what can I do next? I have these two, and there's this diamond, so I must have the top two. Now I have these two, so I must have the top two of this diamond. And it's not so hard to see that once I have a maximal chain, that is, once I have every edge in some maximal chain, then because all of the maximal chains in a Bruhat interval are connected under horizontal diamond flips, that I will actually get everything. So once we have found a maximal chain, uh, we can stop and we know that we've diamond generated. Or we could play it out in this case.
So, in particular, for your diamond, if you have the two left edges, then you must have the two right edges.
If you have the two left, then you have the two right, and vice versa. Yep. Okay, so this is certainly some finite number associated to any interval. And okay, an obvious but important feature of this thing is that it is combinatorially invariant. If I give you isomorphic intervals, this minimum is not so easy to compute, but it's obviously an isomorphism invariant just of the poset. Okay, so we were interested in this, what is essentially the in closely related coefficients of the three families of polynomials. So I will define duv to be the coefficient of the second highest power of q in ruv. Rather, this coefficient is always negative. I want its absolute value is duv. Now, it's possible just from the recurrences that I gave you to deduce these relations. So the coefficient of q in p uv is the number of coatoms of the interval, that is the number of elements covered by v, which are in the interval from u to v, minus duv. And the second highest power in the r tilde polynomial is the length of the interval minus duv. The theorem which implies the combinatorial invariance result is that for any interval in any Coxeter group, in fact, duv equals guv. So this is some kind of combinatorial interpretation of these coefficients, although it's not exactly counting something, right? It's this extremal problem of the minimum size of a diamond generating set. And the reason that we get combinatorial invariance for all of the coefficients of all of these polynomials is that we have these relations, and length is obviously combinatorially invariant. That's just the height of my poset. Number of coatoms is obviously combinatorially invariant. So because this result implies that D only depends on the poset, so too only these coefficients only depend on the poset. Okay, how do we prove this? So I should say this is the exact theorem that Patimo proved in finite type ADE. So he also proved DUV equals GUV. It was known prior to our work that Patimo's proof method works only in finite types ADE. So there is some version of the defining recurrences for the R polynomial that allows certain special reflections to be used, which are not simple reflections, in such a way that you kind of always can you can always be in this case of the recurrence. So this is the case that takes you to subintervals of the interval you started with, and so the recurrence kind of confines itself to the interval you started with, and he's able to use that to prove this fact. That property, which is called the generalized lifting property, that was introduced by Zuckerman and Williams, that is known not to hold outside of finite ADE. So we had some other proof method. So it follows from work of Dyer that DUV is less than or equal to GUV. Dyer had some vector space, some formally defined vector space, and he proved it had dimension DUV. And it's clear that any diamond generating set is a spanning set of Dyer's vector space. And so this inequality is clear. But in order to prove the reverse inequality, we need to construct a diamond generating set of size DUV, thereby proving the reverse inequality. And it turns out that the construction of this diamond generating set is motivated by the recently discovered cluster structure on the coordinate ring of the open Richardson. Although we do not actually rely on any results about cluster algebras because, for example, the cluster structure is only known in finite type, but we are able to just write down this diamond generating set in arbitrary type and show that it does what we need it to do. Okay, so in this example we already looked at, in fact, the example I gave you was a minimal diamond generating set. So GUV equals DUV is 3 for this interval. So computing the various polynomials, the P polynomial should be the number of coatoms, which in this case is 4, minus GUV. So this recovers the 1 plus Q that we saw. R tilde is always monic of degree equal to the length, but the second highest coefficient is what we learn about. This is the length of the interval minus GUV, so this is 3 minus 3, so that goes away. And the R polynomial, GUV is just this coefficient and also the second highest coefficient, because the R polynomial has this symmetric coefficients up to possible negation. Okay. Next, I also want to mention some results of ours related to the Gabber-Joseph conjecture. So just recall that the R polynomials are the point counts of these open Richardson varieties. So if G is a complex semi-simple Lie algebra, I'll write M sub V for the Verma module with this highest weight for any anti-dominant regular integral weight lambda. So yeah, the Verma modules naturally come together in groups indexed by the Val group. These are the blocks of category O, and there are going to be no X between Verma modules from different blocks. So in fact, I might as well just index this by the element V rather than by this weight here. So these are infinite dimensional modules for the Lie algebra, and the submodule relation is exactly Bruhat order. So Gabber and Joseph defined this polynomial, which they called R prime, just to be the alternating graded dimension count of these X groups in category O between two Verma modules. Now, the Gabber-Joseph paper was definitely trying to draw parallels between the R prime polynomials and the R polynomials. In fact, they prove that the R primes satisfy most of the cases of the recurrence for the R polynomials. So people started calling the fact that RUV was equal to R prime the Gabber-Joseph conjecture, although Gabber and Joseph did not explicitly state that as a conjecture. This would be a desirable thing because we have this nice recursive way of computing the R polynomials just by this definition. But the R primes, there's actually no known good way to compute these X groups in general, sort of algorithmically, like the R polynomials. So it follows from Verma's work that the linear coefficients agree, that is, that they're 1 if they make sense, if U is less than V in Bruhat order. Carlin in 86 showed that the top degree coefficients agree, that is, that the R prime polynomial is also monic of that degree. But Bo found a counterexample to the conjecture in 92. So it is not true that R equals R prime in general. However, we prove that the next highest coefficient, Q, the second highest, Q to the length minus 1, we still do have equality between the coefficients of the R prime and the R polynomials. So our name for this coefficient of the R polynomial was DUV. So in other words, dimension of the second highest X group between these Verma modules is DUV. And as a consequence, we not only have this relation between these coefficients, but also, since we prove that DUV is a combinatorial invariant, that also implies that this X group is a combinatorial invariant. That is, if you have isomorphic Bruhat intervals in potentially even different groups, these X groups will have the same rank, as long as the Bruhat intervals are isomorphic. Okay. So I should say really what we prove in order to get this is we prove that DUV is also the dimension of H1 of the open Richardson. This follows because we showed that some of the mixed Hodge groups of the open Richardson vanish, so in general, I can relate a point count, which is the R polynomial. It can be expressed in terms of dimensions of mixed Hodge spaces, but because these particular ones vanish, the only contribution to this coefficient of the point count is actually the remaining piece of H1, which is this H1 equals the entire H1 comma 1 1 mixed Hodge space, and that's why we get this. So also this Betti number of open Richardson varieties is combinatorially invariant by the same reasoning. So it is known in general that the X dimension should be equal to the Betti number of the open Richardson. Okay. Questions about this? Okay. So lastly, I'll say a little bit about this connection to the cluster structure, which motivated our construction, and from which you can get a few more corollaries of our result. Okay, so reflections T are in bijection with positive roots, alpha T. A reflection order, this was defined by Dyer, is a total order on the reflections, so that if I have any triple of positive roots, such that gamma is in the positive cone spanned by alpha and beta, then gamma must appear between alpha and beta in my total order. I guess the way I phrased this should be an order on the positive roots, which are in bijection with the reflections. And what Dyer proved is that if we fix a reflection order, then the coefficient of Q to K in the R tilde polynomial is the number of increasing paths in the Bruhat graph from U to V of length K. Length K meaning they take K steps. Remember that the Bruhat graph included these longer edges that weren't necessarily co-relations. Increasing means that as I take steps in my Bruhat graph, each of those edges is labeled by some reflection. So I want that the root labels of those reflections are increasing with respect to my fixed reflection order. So it is not at all obvious that this is independent of which reflection order you've chosen, but that's true. And in fact, Dyer proved this. So this is a nice, in some sense, this is a combinatorial interpretation for the R tilde polynomial, but it's not useful for combinatorial invariance, at least directly, because we are not given the information of which reflections, which roots are labeling our edges, and so we cannot hope to count increasing paths directly, just given the information of the poset. So just to give an example of this, here's my Bruhat graph for S3. There's two choices of reflection order, this one or its reverse. In fact, in finite type, the reflection orders are going to correspond to reduced words of W naught. So there are two reduced words of W naught in this case. So I told you that R tilde polynomials are always monic. That corresponds to the fact, which Dyer proves, that there is always among the saturated chains, that is among the chains that use only length 1 steps, there's always exactly one of those between U and V, which is increasing with respect to our fixed reflection order. In this case, it's this one. And then there's also one path of length 1, which is trivially increasing because it has only one step. So this dire tells us that this R tilde polynomial is q cubed plus 1. In this case, remember this coefficient here, which is 1, this 1 was supposed to be the length minus GUV. The length is 3 here, so we expect that GUV is 2 in this example. And I'll explain how to get a diamond generating set of that size from this information about increasing paths. So here is the theorem. So fix a reflection order such that the inversions of V are a prefix of the reflection order. So the inversions of V are a set of roots. Those need to be the first so many roots of my reflection order. And let gamma 0 be the unique increasing maximal chain from U to V. So that's the one in red that we saw. We prove that at most one increasing path of the second longest possible length diverges from this one at each point. So that's actually special to this chain and these reflection orders. In general, it's possible to have bad reflection orders, for which this is not true. But this means that if we let FUV be the set of edges of gamma 0 with no such divergence, let FUV be that number, then FUV is equal to DUV. The size of it is equal to DUV, and this FUV is a diamond generating set. So in our example, I have these 3 steps of gamma 0. At the first step, there is some second longest increasing path diverging from gamma 0 at that point, namely the green path. But at this step and at this step, there is no diverging increasing path. So the second and third edges of gamma 0 I keep, and those are the elements of FUV, and there are indeed 2 of them. And we can check that these 2 things do diamond generate the entire interval. So I can flip this diamond, then I can look at these 2 and flip it down, and flip down again. So how would one come up with the definition of FUV I just gave? So recent work of 2 sets of authors. So one, Casals, Gorski, Lesh, and Siementhal, and the other, Glashan, Lamb, Sharon, Bennett, and Spire. They both prove that the coordinate ring of the open Richardson variety is a cluster algebra. So it has clusters, which consist of some frozen variables, which are in every cluster, together with some set of mutable variables in each cluster. So really what's going on is that under the natural bijection between increasing paths, which are the objects I just talked about, and distinguished subexpressions, which are the Deodar style object that these authors use to index their cluster data, the set FUV maps exactly to the frozen variables in their cluster structure. So we learn that there are DUV frozen and length minus DUV mutable variables in each of their clusters. And also, because we have proven that D is a combinatorial invariant, those numbers are also combinatorially invariant and depend only on the isomorphism type of the Bruhat. So we don't need their cluster structure, but certainly this correspondence is how we were able to write down the definition that we used, which in fact works in any Coxeter group. And I'll end there. Thank you.
Thank you very much. Let's thank our speaker.